Swayam Prabha. Digital India. Educated India.
So I want to go back to topic 1.6 and cover a few things there. Cutting me back a little bit? Okay, good. And then I'd like us to look at an interesting version of this market shed frame that we were studying yesterday. So the theme here is, okay, if you're doing geometric nonlinear analysis or second order analysis, so it means the same thing. How do you make sure that you have an analysis that's giving you results that are sufficient? Now, it can depend on what type of element you're using. So let's talk about a few elements, types of elements that are out there. I'm not aware right, if I just think about it right now, of any commercial codes at present that are using the stability function based element. That doesn't mean there aren't any. And certainly this has been implemented by many folks over the years. So we'll talk about stability function elements for a little bit. It seems to me with most of the codes I'm aware of, most of the codes are using a cubic Hermitian type element. We'll look at what that is. But then some codes, like SAP 2000, for example, would, depending on what options you're selecting, will be using either a cubic Hermitian or a P large delta element. So P large delta is also important to understand. So stability function element, what is it? It's basically you set up in terms of the development, you set up the governing differential equations for a beam column member. And typical stability function based solution, it's based on the assumptions that the response is elastic. It's typically done with a prismatic geometry of the member. Euler-Bernoulli kinematics, so no shear deformations. Plane sections remain plane and normal to the axis of the member. And we're considering finite displacements with the stability function based element. But basically, if we're looking at a rotation, we're talking about a planar solution. So basically mainly focused in discussion on planar analysis here. Some comments about 3D. If your rotation, theta, it could be large in general, but the development is such that is based on the assumption that sine theta is equal to theta if you're talking about a rotation of the element relative to its chord between its ends. But and there have been three-dimensional versions of stability function elements, but I think those are even more rare. The plane frame analysis version, we typically start with a matrix relationship that we can derive that relates to axial force. Well, that's just the axial shortening E here is E times EA over L is our axial force. There's nothing special about that. But the other 2x2 parts relate to the moments, where we have stiffness coefficients EI over L. Notice the script L here, so that's an element length. And we have coefficients either SII or SIJ, and so the equations for SII and SIJ are shown here below. How do we get those? We basically we're solving the governing differential equations of this problem based on Euler-Bernoulli beam theory elastic response. And so with this, a term that is prominent within these coefficients, SII and SIJ, is often labeled KL, or sometimes you see it written as kappa L. This lowercase k here is not an effective length factor. This is a different k. In fact, little kl here is basically the square root of P over EI times L. Or if we manipulate that, we can basically say, okay, that's actually pi times the square root of the applied axial load on the element to the PE script L. And PE script L, same notation we've been using the last couple of days. That means pi squared EI over the element length squared. Okay? So with a stability function element, we usually start with this. If we just use the matrix relationship between MA and MB and the end rotations theta and theta B relative to the chords, if we go way back, that's folks would say, "Oh, I'm doing slope deflection equations, and I'm working here with stability functions," right? But then we can transform that 3x3 equation to the equations for a planar analysis where we have two displacements and one rotation at each node. And so the element stiffness matrix is then 6x6. And so that stiffness matrix looks like what you see here. Now, how do we get from the 3x3 to this? Well, for example, if you go back to this one, I say, oh, this 3x3 only is working with relationship between P and E, right there in column 1 and row 1. But I can say, well, hey, I know what the axial force is at the other end. It's equal and opposite. It's also P. Okay, so that's equilibrium. And if we have the two moments here, so I'm not showing shears. Okay, I'm just tracking how the moments relate to the rotations theta A and theta B relative to the chord. Well, clearly, if I have moments MA and MB here and no transverse load in the inside of the element, I can get a shear force. MA plus MB over L is my shear, right? And then equal and opposite to that at the other end. That's all we do to get from the 3x3 to the 6x6, or one part of it. There's a similar things that we can do that are a little more complicated, where we have to say, okay, so here we've got essentially deformations, E, theta A, and theta B, and I want to now relate those to, if I go to the next slide, a general global, but in a local coordinate system tied to the current element orientation. What's the global rotation? What are the global axial and shear displacements at the ends? And so that's really just a kinematic analysis to get those relationships. So if I use, and those are very symbiotic. If I incorporate both the equilibrium relationships, the kinematic relationships that tie all these together, I get the 6x6. Once I also account for an effect of a P large delta that has to go in with all this. So that's a very hand-waving explanation of how we get from one to the other. My approach here that I'm taking in this lecture is not to look at how do we develop these elements and the details that are essentially important, that are essential to the development. It's more of, okay, these are the elements we encounter as practicing engineers. How do we use them? How well do they work? How do we make sure they're working properly? So again, the KL is essentially pi times the square root of P over PEL, and PEL is pi squared EI over L squared. All right, so this plot is fairly informative in terms of what's going on with the stability function element. So those coefficients that I showed you a couple of slides back, SII and SIJ, those depend on the axial load level. So if we, let's take the most basic case. In the limit that the axial load approaches 0, then I get for one of the coefficients, basically goes, or SII goes to 4. Sij goes to 2. Well, that's just the standard 4E/L and 2E/L that shows up with a linear elastic response of frame members. But as I increase the axial compression, those coefficients are changing. So what I'm showing you here is one example of where I'm pointing to a location on the plot. So the values of the stability functions are on the vertical axis. Just the ratio of P to PE is on the horizontal axis. And so if I apply an axial load P that's equal to PE, P over P equal to 1, what have we got? So basically the red curve goes to here, the blue curve goes to there, and interesting, that's the point where those two curves cross. So what these functions are telling us is your tangent stiffness of your element here at this, where it has this particular level of axial force in it. If you try to give a unit rotation here, I'm showing it for theta b. If you try to give it a unit rotation of theta b, you're going to get a moment, or you increment the rotation by theta b, you're going to get a moment of 2.46 EI over L times theta b, not 4. And your carryover moment, if you wish, on the other side, it's not 2. It's also 2.46 EI theta b over L. And so that solid purple curve and the solid red curve, that's essentially showing you how for an element, and here I'm showing with capital L, often with the stability function approaches and traditional practice, engineers would say, hey, I'm using a single element for every member, okay? So that's why I left it at capital L here, but then I showed in the other parts of script L, so it's capital L and script L are the same. Those purple the purple curve and the red curve is showing you how those coefficients are changing, and that's essentially a rigorous solution. It's very accurate representation of what's going on, even with a single element for a member. Now, cubic Hermitian, in this case, it's a finite element based solution. And the solution is achieved by starting out with, so we're going to have a displacement function for the element. We're going to represent the element response by a cubic displacement field along the length. And so then, all right, well, the true analytical response from the differential equations is not a cubic when we have axial force on there, so it's an approximation. But the whole mantra of finite elements is, okay, well, yeah, it's always an approximation, but you need to use enough elements and you have a good solution, right? So the matrices that we get, you get two matrices when you're using a cubic Hermitian element, or we usually write it this way. The first matrix is what engineers often learn in a first structural analysis class, or let's get a first matrix structural analysis class. And so here I'm showing just the fifth column of the element matrix for KE. This is called the elastic stiffness of the element. And so, hey, the fifth column corresponds to a displacement of U5, and so what are all the forces that are produced for a displacement of U5? Or if U5 is a unit displacement, this is telling me I'm going to get shears of 12 EI over L cubed, and I'm going to get end moments of 6 EI over L squared, right? So that's fairly routine, basic result that we learned very early on in matrix structural analysis. But then there's a second matrix here that's called the geometric stiffness matrix, and so it has other terms. Those terms involve the axial load P. And so the geometric stiffness matrix is capturing the geometric nonlinearity, if you wish, or capturing the second order effects, if you want to say it that way, or capturing the P large delta and P small delta effects, if you want to say it that way. And so let's look at that same column of the stiffness matrix here. Again, when you're looking at stiffness matrices, if you take a column of the stiffness matrix, that corresponds to one of the displacement degrees of freedom and what forces are produced associated with displacement at that degree of freedom, right? So in yellow, you can see essentially I'm showing, you could say, a free body diagram, and or I'm showing the forces that we're getting for a displacement U5 there. So if you take a minute to stare at that, look at that as a free body diagram. That's kind of what it is. And you can consider the red dashed P arrow if you wish, or not. Do you have equilibrium? So let's sum moments about the left-hand end in that free body diagram. What do you see? So you have a clockwise moment of 6P times U5 over L, right? And then a counterclockwise moment on that of P over 10 times U5. Okay, and another one at the other end. And so you can say, wait a minute, it's not in equilibrium. Oh, but yes, it is, because what it's doing is it's saying, well, if I have this displacement U5, then the axial force location is shifting. So now I've got an extra moment of P times U5. Okay, so if you include that in writing out your statement of moment equilibrium, say about the left-hand end, you get 0. But that's equilibrium in the deflected geometry, right? So that's what's going on with the geometric stiffness matrix here. And this is representing both P large delta and P small delta effects at the element level via the cubic displacement approximation. So the cubic displacement approximation is giving me some bending displacement relative to the chord. The third element, P large delta, is basically the same elastic stiffness as what we just looked at, but we're going to do a different kg. And I just realized as I'm saying this, I think I thought I fixed it here. Oh, we're good. You were good. I think in what you have and what I posted on the Google Drive, I think I'm circling the wrong rows. So if we look at the second and fifth or columns, second and fifth column here basically corresponds to what you see in the graphic in the yellow. Okay, well that's not in equilibrium unless we consider the fact that, oh, I get a moment of P times delta when this displaces in this fashion, and my geometric stiffness matrix is giving me the P delta shears that would be required to equilibrate that in the displaced configuration, right? But notice this is much simpler than the one we looked at here. So we have a minus 6/5 over 6, a minus 6, we have a 6P over 5L there in the 5-2. We only got a P over L in the P large delta at that location. We've got a P over 10 in the matrix location, the third row, fifth column, P over 10, and in the P large delta, it's 0. Okay, so we're only picking up a P large delta here. That can make it easier to implement. You just kind of slap an easy geometric stiffness matrix on what you're working with, a traditional matrix analysis code. And there's some other advantages that can be a little bit, make the calculations can be a little bit less problematic in some cases in terms of getting convergence, but it may not be converging to an accurate solution. So a couple of examples to kind of illustrate when does p small delta maybe become very, very important. So I apologize, in this case I've left things in terms of kips and inches, or kips and feet. Go ahead. Okay. Yes, sir.
In the Hermitian beam element,
You
said it will consider p small delta effects
It
as well.
does consider p small delta.
So usually the displacement estimates at the nodes are accurate, and in between we are interpolating.
Correct.
Is it because the cubic function, is it able to capture the
Since it's a cubic, then it's capturing the bending relative to the chord, so then you're getting some representation of the p small delta.
but again the internal loads like UDL and all, it will be approximate, not correctly, right?
Yeah, if you've got element loads on the interior, now there's other things going on. And so that for that, in the first day I showed one recommended way that's a kind of a simple way to set it up if you're programming, if you're the software provider or developer. But there's many ways to do that to try to get an accurate estimate. From what I've seen out there, it's, at least when I look at what is displayed graphically, I don't see software providers doing anything other than a first order analysis approximation between the nodes, given what it would be second order forces from the second order analysis at the nodes, but between the nodes they don't consider any p small delta term.
Simply interpolate with the functions.
Yep.
Okay.
Yeah, so this problem, basically it's a cantilever. And so things like a cantilever or a fixed in rotation, that's when we get the most bending relative to the chord, and so the largest p small delta effects. So this example is a little bit elaborate. It involves a lateral load, a vertical load on the column. Again, here everything is in imperial units, and things are set up where the tau factor is essentially 1, but we've got a p over py that's just starting to very slightly become larger than 0.5. So that's where the tau factor starts to become less than 1 in AISC. We've got a pu over pe capital L for the length of this element that's 0.15. A pu over the elastic critical load for the cantilever then that is 4 times that, 0.6. We're showing this as a direct analysis method solution, so with a reduced stiffness. So now if I'm not showing you the derivation of these equations, but if I go to theory of elastic stability and do a differential equation solution for this problem, I can derive, quote, exact moment amplification and displacement amplification formulas, and we can write those in terms of the quantity lowercase u that you see here. And so just very broadly, we can say, okay, well, that exact solution from solving the governing differential equations is that, for all the parameters that I'm giving you here, we've got a moment amplification of 3.45. That's a little bit smaller than the displacement amplification, 3.97. Our first order drift, given the loads here, would be 0.531 inches. Again, that's based on the reduced stiffness. And so if we apply those amplification factors, the exact second order drift is 2.11 inches. The exact moment at the base is 1,340. And this example is contrived to where if you and I take those and we do a direct analysis method unity check of member verification here on this column, this beam column, we get a unity check of 1. So with the exact solution, We're right at what AISC would suggest is you're at capacity. All right, so now the next things I'm showing you here is, okay, so what if we only do a P large delta analysis here? And I'm invoking I'll make a statement here. If we calculate B2 that we looked at the development of yesterday, if we take RM, that factor, remember RM we said that's giving some effect of small delta on the large delta. If we take that equal to 1, then we've essentially not considering any P small delta on the large delta. It's a P large delta B2 approximation. And so that's what I'm doing here in the lines above the blue highlighted box. I'm basically saying if I calculate B2 for that, taking RM equals to 1, instead of a moment amplification of 3.45 and a displacement amplification of 3.97, I'm going to have a single amplification factor 2.61. Okay? Again, this is kind of an example. It shows up in the commentary to the ISC and is like this is kind of an example, worst case of where you have to consider P small delta. You can't just do a P large delta with a single element on this column. But okay, well, what's the ramifications of just doing P large delta here? Well, that's what's in the bottom blue box. What if we just apply the amplification factor of 2.61, we would get 1.39 for the drift, or for the lateral displacement. So our displacement would be off by 34%. You say, oh, that's not good. That's a bit off. But now, how about the moment? The moment is off by 24%. So how about the strength check? We get 0.912. So basically you say, well, okay, the strength check is 9% off. So kind of a worst case scenario, you can say, okay, when it comes down to checking my member strength, all right, yeah, I missed the boat by about 9%. So that's, you can say, yeah, I want to do better than that, but the sky's not falling because I did a P large delta analysis. But that would be with just a single P large delta element for the entire length of the member, which is often what engineers may like to do. If you talk to, say, for example, the engineers at RISA, and you say, here, I've got a problem, and they'd say, yes, the P small delta is important in that problem. You need to use more than one element. And the graph here is an attempt to illustrate that. If you take this member and subdivide it into, what do we got here, 6 elements? It's a P large delta approximation, but you can see that at the element level, there's not much of a large delta. Or another way of looking at this is you could think of you're modeling the P small delta effects in any given member by a bar chain that's attached to the member with an axial load on it, and so the bar chain moves, and so I'm starting to get these destabilizing forces that get thrown into my member. If I use lengths of the bar chain that are very small compared to the length of the member, I'm still going to get a good solution. So that's the key if you're using a code with P large delta elements. As long as you have enough elements, you're good. So how many elements? Some recommendations I'll give you basically relate to aiming for design to get 5% accuracy in displacements, in rotations, 3% accuracy in forces for basically applied load levels at strength up to 70% of the elastic critical load. Usually we don't get any higher, any closer than that in a practical design. And again, we're going to relate to things with different length terms still. So script L is element length, capital L is member length, S is the spacing between sampling points if we're going to try to sample and get internal moments between nodes. So how many elements do we need if we're using the stability function based elements? 1. You've got a differential equation solution, so at least to the extent that you don't have significant shear deformation. It's an Euler-Bernoulli based solution. You're getting a rigorous solution. And we're not solving mechanical springs that have like a switch or something that has some huge displacement in it. Sine theta is equal to theta relative to the chord. So yeah, 1 element is good enough. But again, what goes along with that is, okay, so you used a very coarse discretization of your structure. If you have a case where the internal moments are larger than the end moments, okay, we got to deal with that in some way. And so I showed you a suggested way that a developer or a provider could implement something to get those moments. Or in design, we have this very coarse approximation of B1 that a few of us were talking about here that we looked at the first day, that we apply at the element level to make sure we're covered. Cubic displacement elements, so Mastan is cubic, fast track, E-tabs, if you use the right menu options, GT Strudel, Larsa, SAP, RAM elements, Consteel. Those are at least a lot of the programs I'm familiar with. Those are all have cubic displacement based elements in them, or cubic Hermitian elements. So in this case, if you have something where you have a column, say, that has loads coming into it from the rest of the structure at its ends, but the rest of the structure really isn't doing much in terms of restraining this member's side sway. In fact, maybe it may be destabilizing the member. And so the member is kind of on its own for the most part in terms of resisting side sway. Then 1 element is good enough. If you've got a case where, for whatever reason, the other parts of the structural system may be helping this member by helping to resist its wanting to sway to the side, then it's wise, if you are getting any sense of that, to use 2 elements to capture your P small delta effects accurately. Well, that's pretty coarse. You just 2 elements. But even there, if the axial load level P over PE capital L is less than 0.17, 1 element generally is going to work just fine. Again, the caveat is to avoid the need to have to do something to capture internal second order moments between the nodes and get an approximation there. Okay, well, we would just use a P over PE script L equal to 0.02 or less than or equal to 0.02. And that same goes with the stability function based element as well. If you use an element discretization such that P over PE script L is less than or equal to 0.2, you should be good both with a global solution. Clearly that's a much more dense mesh than the minimum required that I'm showing you here. And you're covering things of not, you can say, yeah, I don't have to worry about having to do some P small delta estimate between the nodes of my analysis solution. Now there is these comments are all related to planar analysis, but everything I showed you in Consteel for out-of-plane buckling, we could do out-of-plane buckling with a 3-dimensional solution. 14 degree of freedom element. If we're starting to get into things where we're doing 3-dimensional solution involving torsion, either a planar solution that buckles out of plane or a spatially loaded member. The recommendation is you really should use at least 6 elements in each unbraced length. In between every position where you got a member connected to other stuff, I would use 6 elements. Okay, what about P large delta? I think there's often confusion thinking about recommendations for cubic elements, but P large delta elements generally require much denser mesh. The simplest rule that works very well is use the P over P script L less than or equal to 0.02 again for this, for P large delta. If you do that, you're essentially assured that you've got enough elements. So what does that imply in general? So as an example, suppose we've got 4 equal length elements representing a beam column, and say P over PL is equal to 0.02, script L. Well, that means I can handle a P over PE capital L of 0.32, 0.02 times 4 squared, right? Or let's say I'm using 8 equal length elements with P over P script L of 0.02. Well, 0.02 times 8 squared is 1.28. So I can get a solution there. I'm confident I've got an accurate solution in that case. If I've got loading that exceeds PE capital L up to 1.28, I should be accurate with 8 elements. Now you could even go larger, but I think you can't get any further. Well, if you keep pushing this, you say, what's the worst I could possibly have? Well, that would be a needing to handle a P over PE capital L of 4. So that would take quite a large number of P small delta elements. Again, for your second order solution, though, we're usually not getting closer than about 70% of the Euler load, because you always have some bending. You've got phi factors or partial safety factors on even your elastic buckling response, so you're not getting that close to the theoretical elastic buckling load. There's one other thing to show you that is something that Dr. Shankar Nair essentially brought to the committees at AISC, and we put into the commentary of the specification. That's that. Let's consider a typical steel buildings. Shankar would say that generally the ratio of your axial load taken by moment frame columns to your axial load in the story that's taken by the entire story, usually that's going to be less than 1/3. Where would he have a design with a steel framing where this is larger than 1/3? Why? Moment connections are expensive, and you're typically going to have a lot of your connections of floor framing to your columns as basically web type connections that don't transfer significant moment. We idealize as pins for the analysis. So if you have PMF over P story less than or equal to 1/3, and if B2 is less than or equal to 1.7, then you can basically argue that your error in neglecting P small delta effects on the large delta is generally less than 4%. Now we can show a derivation of that by using our equations that we discussed yesterday for B2. So we have the RM factor in that equation. If PMF over P story is 1/3, then RM would be 0.95. So now let's calculate B2, but let's calculate it without an RM. That means we're basically doing a B2 that's just handling P large delta. And so if we set that equal to 1.7, that would mean alpha P story to PL story is 0.412. But now let's recalculate B2 given that alpha P story to PL story, with the RM factor in it, which is a conservative representation of P small delta on the drift, oh, we get 766. Oh, that means that's a error of 3.7% by neglecting that those P small delta effects. Not so bad. So Shankar would say, hey, he doesn't have a problem of using RISA and getting his drift and his overall lateral moments in a frame based on P large delta in RISA. And then if he has a situation where he needs to check a non-sway moments and non-sway B1 or P small delta amplification, back to this, but with that being on the length, total length of the member L, where he's just doing a P large delta analysis with one element for every column in the frame, and he would show this and say that there's no problem with that. He may have a conservative estimate with this way of applying B1, but so be it. For most steel building frames, the B1 factor is often 1 anyway, and is not much larger than 1 in most situations. Last thing I want to highlight is if looking at three-dimensional analysis, we can have a 3D frame element, and in software like Consteel, we have a 7th degree of freedom at each end of this element rather than just between 3 translations and 3 rotations. And so what's the importance of that? And so this is a little first order analysis example to try to highlight the importance of that 7th degree of freedom at each node, which basically allows us to model warping in the frame solutions. Now, what's warping? Warping in an I-section member is essentially cross-bending of the flanges. So if we take this simple example here of a cantilever beam, it's built into where everything is fully fixed on the left-hand end there, and then we say, let's apply a torque at the free end. Let's twist it, and so if we look down on it from the top, what do we see when we twist that member? Well, the top flange is being bent in one direction, the bottom flange is being bent in the other. Those two flanges is kind of working like beams, right? That's the warping of the cross section, or the warping is cross bending of the flanges here. And that cross bending of the flanges is really the predominant resistance to twist in most I-section members. We also have the St. Venant torsion, but the St. Venant torsion is a relatively small contribution. So if we solve the differential equations for a first order analysis of this sort of a member subjected to torque, what twist do we get at the free end? So this would be the equation for that. And so again, I have this in imperial units. So this W14 by 22, this is 14 inches deep nominally, 22 pounds per foot, is 10 foot long. And so if we put a 2-inch kip torque on the end of this, we get a 0.052 radians rotation from that calculation. If we neglected the cross bending of the flanges and we just considered what we refer to as the uniform torsion or the St. Venant torsion within the member, then the twist would be equal to TL over GJ. The St. Venant torsion constant, capital J, is very small here. Oh, my in rotation is essentially double. So this is a very simplistic illustration using a first order analysis of warping rigidity is very important when it comes to twisting in these types of structures. And so that's one of the highlights of Consteel is everything in Consteel is based on including that warping. Now, one of my senior colleagues at Georgia Tech a few years back, he's essentially the principal with G.T. Strudel, and he was giving a seminar and complaining about how the AISC spec was really bad because he had an engineer trying to design a boiler building, and G.T. Strudel was having a lot of trouble because he was designing into a range where G.T. Strudel was basically saying, hey, you got a big buckling problem here. Well, a boiler building is something, if you're not familiar with it, is something where the building is basically housing a boiler, and so it's a big boiler on the interior. You have nowhere to brace your columns because there's a big boiler there. They go way up, and you're supporting the boiler from the top of the building. Okay? And so you basically got this very long unsupported length of your columns there of the building, at least in the direction in and out of the plane of the wall of the building. And so that's basically a case where most of the software out there, very few of the software packages at present will actually give you that 14th degree of freedom and give you a realistic representation of what's the torsional stiffness here. Now, in a lot of designs, it doesn't matter because torsion is a very minor player. The members are relatively short before they're connected to other stuff. And so life is, ignorance is bliss. We don't really notice the fact that the torsion approximation is very poor. Things are okay. But in a case like this, in that boiler building, because the element that G.T. Strudel was using was only based on GJ over L for the torsional stiffness, no consideration of warping. Well, hey, if we designed steel and we only counted on GJ over L in the resistance equations, we wouldn't be designing steel very long because we would have to use a heck of a lot more steel to get it to work. The ECW term in the resistance equations is essential to lateral torsional stability. What this plot here is showing is if we even just take a very basic W14 by 22 that's a little more than 10 foot long and simply supported torsionally and flexually at its ends, and if we look at a rigorous elastic buckling solution, neglecting the warping rigidity, the cross bending of the flanges, and using a 0.8 stiffness reduction from direct analysis method, the strength that we would get from theory, neglecting warping effects, would be the interior red curve there. The blue curve is basically what the AISC specification would say, that's our strength envelope. So you set up, you run your structural analysis, a 3D analysis. You look at this. This member doesn't look too out of the ordinary here. And your analysis comes back, it's failing and saying that you've got significant elastic buckling of your members at a very low load. Why? Because you didn't include the warping. And so the recommendations that relate to that, in cases like this, then it's wise to consider using a, quote, effective member GJ that incorporates warping. So actually RISA does this, where they have an option where the program's only using a GJ, but they derive a increase in GJ that accounts for the warping stiffness. So it's kind of a backdoor representation of warping that's approximate, but it keeps things out of trouble with problems like I just showed you. This is also suggested. I do a lot of work also in the steel bridge arena in the United States, and I've been involved a lot with design of horizontally curved eye girder bridges. Well, horizontally curved eye girder bridges, you've got torsion is very important. It's an eye girder, and if you're going to do a grid analysis of such a bridge, if you do that with just a GJ over L, you're going to run into trouble sometimes where you say, why are my deflections so huge? Because you don't have a good model. So there's similar recommendations in the American AASHTO design standard for bridge construction that say, hey, for grid analysis, you can use it's a rough approach, but you can use an equivalent GJ to get a solution that's a reasonable solution. Or ideally, if the world had Consteel or other programs like that, the warping is included within the solution, and you've got something that can be used very naturally and very directly. You have any problem where you've got a significant torsion on an eye section member,